Hi, welcome to Chapter 4 of Material Science. This week we are moving on to insulators, an absolutely essential part of every electronic system. So, what exactly do insulators do? Simply, they stop electrical current from flowing where it shouldn't. Think of them as traffic barriers that keep electricity in its proper lanes. Their job is to isolate components, protect circuits, and keep everything running safely. And what makes them special is how their atomic structure resists the movement of electrons. That resistance is what gives insulators their unique properties. Throughout this chapter, we'll look at how insulators are designed, why they are so effective, and how the science behind them translates into real world applications. Let's take a closer look at what makes insulators so special. Unlike conductors, insulators have extremely low electrical conductivity. That means they really resist the flow of electricity. If you glance at the table on the right, you will see conductivity values for typical insulators range from 10 to the power of negative 10 all the way down to 10 to the power of negative 15 ohm inverse matter inverse. That's incredibly low. This low conductivity comes from something called an energy band gap. Basically, a large gap that prevents electrons from jumping into the conduction band. For insulators, this gap is usually greater than 2 electron volts, while in metals it's basically zero. Now, here's a cool fact. About 8% of industrial ceramics fall into the insulator category, especially those used in electronics. Things like transformer cores and radio magnets in loudspeakers rely on these materials because of their magnetic properties and their ability to resist current. So, while they may not carry current, insulators are carrying a lot of weight in modern technology. All right, let's talk about the electrics. These are materials used in insulators, especially in things like capacitors. The image shows a basic setup, a parallel plate capacitor, where we apply voltage to two metal plates with an insulating material or dielectric sandwiched in between. Now, what actually happens inside the dielectric? When an electric field is applied, tiny dipoles inside the material line up with that field. This causes charge to build up. We describe this buildup using something called charge density, and it increases as the electric field increases. There is a key relationship here. Charge density equals the electric permittivity of the material multiplied by the electric field. For vacuum, we use a constant called epsilon naught, around 8.85 times 10 to the power of negative 12 farads per meter. When we use other materials, we multiply that by other constant called kappa, the electric constant. This tells us how well that material can store electric energy in the field. So, in short, the electrics do not conduct electricity. They help manage it by storing energy and controlling how electric fields behave inside circuits. Let's continue with more dielectrics, specifically dielectric strength. Every dielectric material has a limit to how much voltage it can handle before it breaks down and starts conducting electricity. This limit is called dielectric strength. If you exceed it, the material fails, the current flows through it. On the right, you can see a table that gives us real examples. Materials like alumina, beryllium oxide, nylon, polyester, and others. For each material, we are given two important numbers. The electric constant, which tells us how well it can store energy in an electric field, and the electric strength, which is measured in kilovolts per millimeter and tells us how strong the material is against electrical breakdown. Also, we should note something about the atomic structure. Materials that have more than six free electrons in their outer shell usually have those electrons tightly bound to the nucleus. That's one reason they don't conduct electricity well. But no insulator is perfect. Under certain conditions like high heat, high voltage, moisture, or contact with other materials, they might start to conduct a little current. So the electric strength and constant help us figure out where and how to use these materials safely in electronics. Even though we call these materials insulators, no material is a perfect barrier to electric current. All insulators allow a very tiny amount of current to pass through. But when you keep increasing the voltage applied to an insulator, the current increases as well. Eventually, you reach a point where the material can't block the current anymore. It becomes fully conductive. That point is called electrical breakdown or insulator puncture. Take a look at tools like pliers used in electrical work. You will often see a voltage rating printed on the handle, like 10,000 volts. That means that the plastic used on the handle can insulate up to 10,000 volts. Beyond that, the material might break down and allow current to pass, which can be dangerous. So, in real world applications, understanding the breakdown voltage of insulators is key to keeping electrical systems safe and functioning properly. Now let's take a closer look at different types of electrical behaviors in insulators. First up is resistance to leakage currents. Sometimes impurities on the surface of an insulator allow a tiny amount of current to leak through. This is called leakage current. A good insulator should resist this, which we call leakage current resistance. Next, dielectric strength. This tells us the maximum voltage an insulating material can withstand per unit thickness before it breaks down and conducts electricity. Then there is thermal leakage. If there is foreign matter inside the insulator, it can create a path for a small leakage current. That current starts to heat the material. As it heats up, even more current starts to flow. This cycle continues, and because heat is involved, we call it thermal leakage. Lastly, we have erosion leakage. Sometimes during manufacturing, tiny microscopic cracks or gaps can form inside the insulator. These defects allow small amounts of current to leak through as well. That's erosion leakage, and it's another factor to watch out for in material quality. All these factors remind us that even the smallest flaws can affect how well an insulator performs. Let's finish our discussion on the electrical properties of insulators with three more important points. First, we have the electrical resistance value. This is the amount of resistance a material shows when a voltage is applied. When we calculate it per unit size using measured insulation resistance, we call that the specific resistance of the insulator. Next is the dielectric loss factor. When insulating materials are exposed to electric fields, they can't completely block the current. Some of it turns into heat. This is called dielectric loss. The amount of loss uh, uh, depends on voltage, temperature, and especially frequency. As frequency increases, the electric losses usually go up too. That's why we use special insulation materials like polyethylene in cables for high frequency applications. Lastly, there is something called arc resistance. When an insulator is hit by an electric arc, a sudden burst of current, it might allow some current to pass through. The only way to know how much it can handle and how it might change after the arc is through testing. These factors help engineers choose the right insulating material for safe and efficient performance in electrical systems. Let's now talk about insulation materials. They are the silent protectors inside every electrical system. These materials are designed to stop unwanted current and make sure everything flows exactly where it should. Think of them as bodyguards of your circuits. They can be as simple as rubber coatings or as advanced as a complex polymers. But no matter their form, each is carefully chosen for one reason: its ability to contain and control energy. We use these materials to protect people and devices from electric hazards, keep systems performing reliably, and make sure electronics last longer. In this section, we are going to break down how these materials are selected, what makes them special, and the science behind how they work so effectively in the worlds of electrical engineering. Beryllium oxide. This material is a white, solid substance that looks and behaves similarly to ceramic. It's known for its excellent insulating properties, especially in situations where high thermal conductivity is also needed. That makes it perfect for use in high-power electronic circuits, particularly in the form of heatsink flakes used for insulating semiconductors. But there's a serious health warning here. Beryllium oxide is toxic. If its powder is inhaled, it can cause serious lung diseases. So, while it's a powerful and effective insulator in the right applications, it has to be handled with extreme care. ABS is a type of plastic. The combination gives ABS good strength, durability, and a high dielectric strength, about 20 megavolts per meter, which makes it a great insulating material. ABS is widely used in outer casing of electronic devices and appliances, like the housing of a hand mixer or a motor. It provides both electrical insulation and impact resistance, making it ideal for protective enclosures. Acetate is known for its excellent electrical insulation properties, which makes it a reliable choice for electrical safety equipment. It's especially useful in applications where insulation is critical to prevent unwanted current flow. Beyond electronics, acetate is widely used in the film industry. particularly in the production of cinema reels and microfilms, thanks to its transparent and flexible nature. So it's not only protective but also versatile in how it's applied across industries. Acrylic is commonly used in areas where both strength and transparency are important, along with good insulation. You'll often find it in illuminated signs, automotive tail lights, and various lighting units. So it's not just durable, it also looks good and serves as an insulator, making it a great choice for both practical and aesthetic applications in electronics and lighting. Most ceramics are made from oxides that include a combination of material and nonmetal elements. What makes them special is their excellent electrical insulation, even under high temperatures. That's why ceramics are widely used in the production of resistors and capacitors in electronics. So, when you need something that can handle heat and electrical isolation at the same time, ceramics are the go to material. Glass is made by melting materials like silicon, sodium, potassium carbonates, and metal oxides like lime and lead oxide. It's usually transparent and shapeless, but when heated, it can be molded into different forms. It's quite resistant to water, oil, and acids, making it a great insulator. However, glass is also brittle and it can crack easily under sudden temperature changes, so there's something to keep in mind when designing with it. Porcelain is made from white insulating soil that's been baked. It's waterproof, durable, and hard. One of its standout features is that it's not affected by sudden temperature changes. Anywhere from 0 to 100 degrees Celsius, it's also resistant to acids. Porcelain doesn't conduct heat well. It transmits very little of it, and just like glass, it's brittle, so it can break under mechanical stress. PVC is probably the most commonly used insulating material out there. In its pure form, it behaves like glass. That means it's brittle. But when mixed with things like oil, it can become flexible and plastic like, especially when heated. Most cables that carry electric current are coated with PVC for insulation. It's also widely used to make electrical and electronic device casings, thanks to its insulating properties and flexibility. Let's take a look at gas insulators. Gases do not conduct electricity unless they are ionized. That means they only become conductive when a certain voltage causes an electrical discharge. This ionization point depends on a few factors like temperature, pressure, or even the shape and distance between electrodes. Normally, the electric constants of gases do not vary much at room temperature. They are all pretty close, within about 3% of each other. But when pressure increases, the electric strength of gas actually decreases. So gas insulation is great, but is sensitive to its environment. Air actually works as a natural insulator in high voltage systems, like in power lines. But here's the thing: if the air contains dust, coal particles, or moisture, its ability to insulate drops and its conductivity increases. That's because these impurities help electricity to find a path more easily. Even though air can insulate on its own, it also acts as a core insulator medium in devices like capacitors and transformers, as long as it's clean and dry. Liquid insulators. There are two key types we use in electric systems, switch and transformer oils. Switch oil is used in devices like switches that generate heat and arc during operation. Its job is to quickly remove the heat and help extinguish the arc as fast as possible to avoid damage. On the other hand, transformer oil plays a double role. It works both as an insulator and as a cooling fluid for in transformers. Most of the time, this is a type of mineral oil designed for electrical use. That brings us to the end of the chapter for insulators. We have explored how insulators play a critical role in electrical safety, from preventing unwanted current flow to ensuring the durability and efficiency of devices. Whether solid like ceramics and glass, liquid like transformer oil, or even gases like SF, these materials are designed to resist electrical conduction under normal conditions. Their properties, such as the electric strength, thermal resistance, and durability, make them essential in everything from high voltage power systems to everyday electronics. Now, in our next chapter, we will shift our focus on semiconductors. These are fascinating materials sit between conductors and insulators, and they are the foundation of all modern electronics. We'll dive into how semiconductors work, what makes materials like silicon and germanium so special, and how we can manipulate their properties to build like diodes, transistors, and integrated circuits. So see you on the next chapter.